everyone. Welcome to a new virtual tour of ESO's Paranal Observatory. My name is Hector Salas, and I will be your guide today, together with Felipe Zurita. Felipe, how are you?
Hi, Hector. I'm Felipe Zurita. I have a grade in astronomy. Today, I'm producer and show you all things about the Paranal, shorts, and videos, and and have the comments you leave. You can the people see us can leave the comments, readings, wherever you want to know about astronomy, whatever you want about the space, the stars, galaxies. You can ask and leave in the box comment. How are you, Hector?
I'm fine. Happy to be here once more time. Allow me to introduce myself for our audience. I'm Hector Salas. I'm a PhD student at the Leibniz Institute for Astrophysics in Germany, and I have been a member of the team of tour guides for Paranal Observatory since 2019. Back then, I was doing my master's in Antofagasta, and I was part of the team that do the in-person tour of the observatory. And right now, I'm doing my PhD, working mostly on topics related to galaxies. And I will be your guide today, and Felipe will be our producer. And as you say, if you have any comments, any greetings, questions, you can leave them in the comment box, and we will answer them at some point during the tour. So let's start first by talking about ESO. So ESO is an international organization that is comprised of 16 countries that you can see here on the screen. Originally, there were only 5 of them, all from Europe. And now you can see there on the screen, we have a couple of non-European countries, but let's go to the list. So we have Denmark, Netherlands, United Kingdom, Ireland, Belgium, France, Portugal, Spain, Sweden, Finland, Germany, Poland, Czech Republic, Austria, Switzerland, and Italy. And we also have Australia. Australia recently joined as a strategic partner. And we also have Chile. And Chile is the host country, the telescope that ESO control are built in Chile. Now, some people sometimes confuse ESO with the European Union. These are different things. We have some non-European Unions members of ESO, like the United Kingdom. And we also have the non-European countries that we already mentioned, Chile and Australia. All right, so what is the mission of ESO? The mission is to design, to build, and to control astronomical instruments and observatories to incentivize the new scientific discoveries and the collaboration in the field of astronomy. Now, in the 60s, ESO was looking for places where to build new observatories, particularly in the southern hemisphere. And at the same time, Chile was looking to attract human capital to the country. And here on the screen, we have the different observational facilities of ESO in Chile. So the first one was La Silla Observatory in the 60s. And La Silla is in the La Serena and Coquimbo regions in Chile. Their star telescopes are the ESO 3.6 meter telescope and NTT, that is the New Technology Telescopes. And it's a very nice observatory. I have the opportunity to observe there once, not with the ESO 3.6 meter telescope, but with a smaller one. But it's a very nice place. And that was the first one that was inaugurated here in Chile. And then in the northern part of the country, we have in the area of Changnan-Tor, we have ALMA and APEX. Now, APEX is a precursor of the technologies that were later used in ALMA. It's an antenna for radio astronomy. And ALMA is not only ESO control ALMA, but it's a consortium of ESO plus the United States, plus some countries from Asia Pacific like Japan. And it's an international collaboration. So ESO is just a part of the team of ALMA. And more to the coast, we have Paranal and Armazones. So Paranal is the place that we're going to visit today. And there we have the BLT, the Very Large Telescope, and the BLTI, that's the Very Large Telescope Interferometry. In addition to that, we also had the telescope PST and VISTA. Those two are survey telescopes, and that means that instead of focusing on a specific target that somebody wants to study, they create maps of the whole sky. And you can use that to look for things that are moving or changing brightness, and that are very cool. And the ELT is being built currently in Cerro Armazones, very close to Cerro Paranal. It has already been past the 50% benchmark of build, and it will be finished in a couple of years. It will be the largest telescope ever built, and in between this, the area of Paranal and Amazonas, we have CTA. This is an array of telescope that is being it's going to be built and it's going to be specialized in the detection of gamma rays. So now that we have a bit of an overview of the different ESO facilities in Chile, let's travel to Paranal Observatory. So here we are digitally traveling across the Atacama Desert. We are more than 1600 kilometers north of Santiago, the capital of Chile, and we are about 200 kilometers south of Antofagasta, the regional capital. The nearest city is Taltal. Now, here we are seeing in the background Paranal Mountain. Paranal Mountain is 2,600 meters above the sea level, and it's part of what is called the Coast Mountain Range of Chile, or La Cordillera de la Costa. And in the background, you can see a bit of a haze. Those are clouds. So you might wonder why in this desert, that is one of the driest deserts in the world, why do we have clouds in the background? Okay, that is because of the influence of the Humboldt current. Here we are just 12 kilometers away from the ocean, from the Pacific Ocean. And the Humboldt current is a mass of cold waters that come from the Antarctic and goes through the coast of Chile and Peru and makes the ocean there very cold. So it's not like the Caribbean waters, but it's a very cold water. And this also produces an effect known as thermic inversion. And what this causes is that all the humidity stays below of 1,000 meters. All the clouds from there. And here, since we have here the coast mountain range, this prevents these clouds to come further inland. And we also have another natural barrier here that helps to create this desertic landscape that we have here in the north of Chile. That is the Andes. And the Andes are to the east, the opposite direction. And the mountains there that are over 6,000 meters in height, they block the humidity and clouds coming from Argentina and Bolivia. And the result is a very dry and arid place. Let's change our view and let's get closer to Paranal Mountain. So here we can see that the top of the summit of the mountain has been got. We have a road, we have our telescopes, and you can see the different names there. And I would like to comment to you that Paranal in the Quechua language means whirlwind. And this is possibly a reference to the whirlpool that sometimes form in the desert due to wind. But usually the sky here is very calm and it's very clear. This is one of the best places for astronomy inside the Earth. To get better conditions, you have to go outside with a space telescope. So let's set foot on top of Paranal Mountain. And here we are in this 360 tour. So let's first turn around and look at what we have here. So we have the big 4 telescope here. Over here in the distance, we can see the clouds. Below those clouds is the Pacific Ocean. And if we keep moving, we are now looking toward the south. We have this beautiful desert landscape. And now we're looking toward the east. And here we can see in the distance the Andes. And here we have the place from Armasares Mountain. And you can see here there is an arrow. That is a volcano, Volcano Yuyayaco. That is actually the border with Argentina. Chile is a very long but narrow country, and we're actually one of the widest part of the country, but from here we can see the border with Argentina. Now, let's focus on the telescopes. Okay, so we have very big telescope here. These 4 big ones, they are the BLT. The BLT is not a single telescope. It's these 4 telescopes that we have here. Each one of them has a primary mirror that is 8.2 meters in diameter. And they are UT1, UT2, UT3, and UT4, where UT stands for Unit Telescope. In addition, we also have 4 auxiliary telescopes, or AT. We have one here. Here we have another one, a third, and a fourth. They have a primary mirror that is 1.8 meters in diameter. So about like a height person, if you want to compare with something. And now, the four big telescopes, they can work independently, observing different objects, but they can also work together using what is known as interferometry. The four smaller ones, they only work using interferometry. And if you can see here, there are some tracks here. This is because the auxiliary telescope, they can move, and we can put them in any of these 30 stations that we have here, these octagonal doors. You can open them, and we can send the light of the telescope underground to some underground tunnels. And all of this is for doing interferometry. And we have some as video that we can use to clarify things here better. So when we do interferometry, the telescopes are observing the same object in the sky, and we combine the light to generate a virtual mirror that is similar with similar characteristics to the maximum separation between the telescopes. So if we use only the four big ones, we have a separation of 130 meters. With the four ETs is 200 meters. And the light is sent to underground tunnels and combined in the interferometry building, that is the center building on the image. And this is done in an analog way. The light is sent using mirrors and tunnels. This is not a post-processing thing. The light is combined completely analog. Now, why do we do this? So as I said, the virtual mirror that we're creating is similar to the maximum separation of the telescope. In interferometry, we call this the baseline. And what we're mostly interested in here is gaining a better resolution. What does this mean? That we can see better details. So, for example, if two stars are very close in the sky, with interferometry, we can increase our resolution and make it so we can differentiate these two stars instead of seeing as just one star. Unfortunately, you cannot improve the amount of light that we're collecting because that depends on the area of our mirrors. This is like putting a bucket on terrain. The larger your bucket, the more rain you can collect. The larger the area of your mirror, the more light you can collect. And this means that you can see objects that are fainter, and they can be either intrinsically fainter, or they can just be much more farther away. Now, the four telescopes, in addition to their designation as UT, they have been given names in the Mapudungun language, that is the language of the Mapuche people, the natives of the south of Chile and Argentina. And in that language, we have here Antu, which means the sun, that is UT1. Then for UT2, we have Cuyen, the moon. Then for UT3, we have Melipal, which means something like four stars and is a reference to the Southern Cross constellation. And finally, we have Jepun, which means something like the evening star and is a reference to the planet Venus. Now, because of time constraints, we cannot enter to the four big telescopes, but do not worry, they are structurally speaking the same on the inside. The only difference is that they have different instruments. Each one of them has a capacity for three instruments or three cameras if you prefer, and they are all different. So we're going to go inside UT3 or Melipal. So here we are inside the telescope, and let's start by just looking around. And you can see here some people. These are some engineers that are working during the day doing some maintenance, but they also help us to have a sense of the scale here, of how big this is. We are here in what would be the fourth floor of the telescope, and we can see here the primary mirror is 8.2 meters in diameter, made out of a single piece. There are some larger telescopes, but they are using segmented mirrors. This is a monolithic mirror. It's made out of a special material called zero dur. It's a mix of glass and ceramic, and it's only 17 centimeters in thickness. And what gives the reflectivity here is a very, very thin layer of aluminum. And I'm talking about like nanometers thick. So this is thinner than a human hair. Now, the telescope has three mirrors. So this is the primary one. On top, we have the secondary mirror. And then we have a third mirror that you cannot see too well in these images, but it's here at the center. And as I already mentioned, there are three instruments here. We have one here. This is BIMOS. There is one below, and one on the opposite side that we cannot see in this image. So how did this work at night? Well, first we need to open the enclosure, and the doors or the window is over here. So it's this part over here that goes all the way to the ceiling, sort of in a L shape. And this white part over here is actually a wind curtain. Now, if we want to point to some place in the sky, we need to move the telescopes. This telescope has two possible motions. So the blue part, or with the mount of the telescope, is fixed, and this part can tilt. That's one motion. The other motion is, well, if you take a look here, this part of the floor is separated from the rest. And this is because this part can rotate in 360 degrees. So combining this rotation with the tilting, we can point at any point in the sky. And we have a small video showing the path that the light follows when we're doing observations. Okay, this is obviously exaggerated. We don't open the enclosure this much, and it's not floating in the sky. Okay, so when we're observing, the light is going to come from the stars. It's going to hit the primary mirror, that is a concave mirror. Then it's going to go to the secondary mirror, a convex mirror, and then to the third mirror. And the third mirror is the responsible to send it to an instrument. You can rotate it so you send it to the right or to the left, or you can just let it go straight down to the third instrument. And this way we can choose which instrument we want to use, and we can only use one at a time. All right, so let's get back to the telescope and let's change our view. Let's go downstairs. So here we are below the telescope, and here we can see the instrument that is below. In this case, is Symphony. And here we have this white cell structure that supports the mirror. The mirror plus this white structure weighs at about 22 tons. This is very heavy. And it's actually so heavy that if the mirror were to be made of glass, like the same mirror that you have in your house, when you tilt the telescope, the stress will be so high that the mirror would break. So the solution was to use this zero-dur material, and this zero-dur material is somewhat flexible. So the stress caused the mirror to deform a bit instead of breaking. Now, this is a problem for the quality of the images. So here's when the active optics techniques come into place. So if you take a look here, we have some gray boxes here. These are the so-called actuators. There are about 150 of them in the mirror, and they are like pistons. They can push or they can pull. So we have a system in place that is actively checking the shape of the mirror, and then we use the actuators to correct that in real time. So hence the names of active optics. And this allows us to have a much lighter mirror. This is one of the two technologies that make Paranal Observatory the most advanced for astronomy. The other one is the adaptive optics that is used to correct for the atmosphere. I guess everybody has seen the star twinkle. Well, this happens because the light goes through different layers of air that have different densities, different temperature, and this causes the light to sort of move in random ways. The solution is the adaptive optics, and for that we observe a star in our field of view that we know how it should look in our images, and then we apply the necessary corrections. And if we don't have a star in our field of view, well, then we have to use some lasers. Only the UT telescope has the lasers, the other ones don't have them. And what these lasers do is they each of them to the atmosphere to a layer of sodium that is very high in the atmosphere. The sodium atoms get excited and then they start to emit light. So we create an artificial star and we know how it should look on the images so we can apply the necessary corrections. And so those two techniques, the adaptive optics and the active optics, make this observatory one of the most advanced in the world. So let's go back up. And do you have some questions so far,
I'm
Felipe?
reading only readings today, but the commonly question about this telescope is how far can see in the night.
Yeah, a lot of people ask that, and for me, it has always been a bit of a complicated question to answer because how far can you see? It depends on many things. It's going to depend on, well, how much time are you observing? So the longer your observation, the more light you can collect, and you can see things that are further away. So that's one thing. Now, usually you don't want to do a very long observation. So what you would do is you would break this in different sections. So you can observe for, I don't know, 20 minutes or 15 minutes, and you do 10 of these observations. So you have 10 observations of 15 minutes. Then you had, when you add it up in post-processing, you can have an image equivalent to 100 minutes, 150 minutes of observation. And this will allow you to see fainter objects that are farther away. But also it's going to depend on our ability to collect light. So the larger your mirror, the farther away you can collect. And this is one of the reasons why sometimes astronomers refer to classes of telescopes. So Paranal Observatory has 8-meter class telescopes because these telescopes have a primary mirror that is 8.2 meters in diameter. And sometimes you will hear something about talk about a 4-meter class telescope. And that will give you an idea of how much further can you observe, but also how long you need to be observing to reach that level. But to give a more simplified answer, you can go very far. For some time, Paranal had the record of some of the farthest objects discovered. Now, those records they don't hold anymore, especially since the new results from James Webb Telescope that shattered all the records that we have in distances. So I hope that gives a bit of an idea for that. And I remind everybody that you can put your comments, your greetings, your questions, and we will try our best to answer them.
That's right.
So,
What is the next part?
okay, the next part is going to be the control room. But before we go there, I want to comment on something else that is usually asked here. That is, how do you clean the mirrors? Or do the mirrors get dirty, or do you need to do some maintenance to them? And the answer is yes, we need to clean them. So what we do is that an engineer will use this crane, we will tilt the mirror, and we spray it with a foam of carbon dioxide. This foam will come down because of gravity, and it will drag any dust particle. That's the easy way, and it's done every other week. The more complicated way of doing it is what is called the recoating process. So for that, we use this yellow crane or yellow lift that we have here to remove the mirror plus the white structure that supports it. We take it to the base cam. The base cam is somewhere over here. And then in a special chamber, we remove the aluminum layers. And then in a different vacuum chamber, we put a new one. That is done every 18 months. But it's done in sequence. Is we do it today for here. 18 months later will be the turn of UT2. And then 18 months later for UT3, and so on. Okay, so our next stop is the control room, and that is this building over here. So at night, everything has to be completely dark inside the telescope because any source of light can contaminate scientific observations. So there is no one inside the telescope. So this more romantic notion of the astronomer looking through the ocular, that no longer happens. That's more for amateur astronomy. But for professional astronomers, they usually are in a separate control building. And that's one over here. So here we can see the building from the side. Are we going to go inside here? So in addition to the control of the different telescopes, there are also some other offices here. And here we can see the area that is used to control the telescope at nights. And if you take a look here, we have a small sign here that says UD4. This is because this entire area with all these screens, all these computers, is just to control a single telescope, namely the UT4. If we keep advancing here, we have the area for UT1 over here, and then we have the area for UT3 and UT2. So we go here. Here we're inside the console that controls the UT3 telescope. And by the way, here we have a nice picture of the laser spin shoot for adaptive optics. So if you see all these screens here, all these computers, you may think a lot of people must be necessary to control these telescopes, but that is really not the case. At night, there will be only two people here. It's going to be an astronomer and an instrument and telescope operator. So these telescopes, they are very technologically advanced and they're also very expensive. So people don't trust the astronomers that they're going to be capable of handling them. There is a specific job that is to control and manipulate the telescope, and that is the job of the telescope operator. The astronomer is there just to supervise the science. So we can think of this as a pilot and a co-pilot in a plane or in a rally car. So the telescope operator, he's the pilot, he's handling the machine, and he's in charge of that. The astronomer, he's the co-pilot, he has the map of what we're doing tonight. He supervises the science. So if only two people are going to be here at night, why so many computers? Well, you have to remember each telescope has three different instruments, and we're going to have dedicated computers to control each instrument. Maybe also a different dedicated computer just to control and move the telescope. We additionally need extra screens for information, for example, weather information. If the weather conditions are not the correct ones, or we need to close down. And here usually the problem is not clouds, is wind. If the wind speed is too high, it could be dangerous. For example, a small pebble could be lifted up by the wind and then crash into one of the mirrors, and there are no replacement for the mirrors. So that will put one of the telescope completely out of commission. So if the wind speed is too high, we have to close down. And we also need to close down in case of high humidity of rain, for example. But usually the conditions here are very good. We have over 300 clear nights a year. And the telescope, it operates the whole night. Observations start before sunset, before, and they stop after sunrise. Now, what do people have to do to be able to observe here? And who can observe here? Well, astronomers from every country in the world can use this facility to do science. But they need to apply first. There are a couple of times a year when they need to send their observational proposals. And these proposals, they have to be very complete. They got to say They need to say not only what objects they want to study and why, but whether there are previous observations of these objects and with which telescopes. They also need to say how many hours of observation they might need for their required science, how far away the moon needs to be so it doesn't distort the quality of the scientific observation, etc., etc. And then a committee decides to who give the observation time based only on the science of the proposal. The best science wins. And this is highly competitive. On average, we receive 7 or 8 times more proposals than there is actual time to allocate during the year. And for some instruments, this is even more competitive. Like for Muse, for example, an instrument in UT4, they sometimes receive over 20 times more proposals than is time to assign. Okay, so if you get lucky, you had a very good scientific proposal and it got accepted, then there are two modes that you can have your observations. There is this visitor mode and the service mode. In the visitor mode, you get to travel, you sit here on the chair, and you supervise the science. In the service mode, you do not get to travel, but you give your instructions to an astronomer of the ESO staff, and they supervise the science for you. Once the observations have been acquired, they are private for the astronomer that sends the proposal for about 1 year. After that, everything is made public, and anyone can go into the ESO website, create an account, and download the scientific observations. Now, astronomy is a very collaborative science, so what you will do is you would contact the astronomer that requested the observation, tell them what you want to do with them, and they will usually say, yes, totally cool, do your thing, And sometimes, if they're very much interested in what you're doing, they might request to join your team and help you with your scientific project. So I think this is a very good time to start talking about what are the scientific discoveries that have been made, not only of
That's
Paranal
right.
Observatory. Mhm.
I have the video of top 10 of principal discoveries made for ESO. So let's start to see what is kind of discovered. Let's
All
start
right.
the video.
Observations with ESO telescopes have led to many breakthroughs in astronomy and, over the years, have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at Lucia was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang Theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when two independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
All right, that was our top 10, but we have an extra result, a bit of a bonus track. A team of astronomers captured the first image of a supermassive black hole. Felipe, we can, there, thank you. So, the Event Horizon Telescope, an array of 8 ground-based telescopes distributed throughout the planet, coordinated by an international collaboration, achieved the first direct visual evidence of a supermassive black hole and its shadow. The image reveals the black hole at the center of Messier 87, a massive galaxy in the nearby Virgo galaxy cluster. This black hole is 55 million light-years away from Earth and has a mass of 6.5 billion times that of the Sun. So a very spectacular image that we can see there on screen. Alright, I hope you enjoy your list of top 10 discoveries made with ESO and the scientific staff behind them. And I would like to remind everybody that we not only have these virtual tours every Saturday of Paranal Observatory and La Silla Observatory, but we also have in-person tours every Saturday. For Paranal Observatory, there are tours every Saturday, one at 10 a.m. and the other one at 2 p.m. These are completely free, but you need to register first in a website. Now, the other thing is that you need to come to the observatory by your own means. So there is no transport offered. Otherwise, anyone can come. It's completely free. Children above 4 years old, if I remember correctly. And you can enjoy this beautiful place and the science behind it. And you get to go inside the telescopes and enjoy it. And for the Silla telescope, Felipe, maybe you can tell us a bit more about that.
La Silla, you can visit every Saturday and Sunday because in the winter days only having the in the morning the visit, but you can visit every Saturday and Sunday in the years. So you can come to the ESO.org and go to the part of visit La Silla or Paranal.
All right, thank you, Felipe. So that you have it. If you have the opportunity to travel to Chile, maybe consider adding this to your list of destinations. Okay, so one thing that you cannot see in the in-person tours in Paranal is the night sky from the main platform. But we can do this using the power of this virtual tour. So here we can see the beautiful night sky in Paranal Observatory, and it's not even completely dark. We can still see some traces on the sunsets over here. And sunsets on this location are very beautiful. So let's talk about what can we see here in this beautiful sky. And let's start for one of the most easily recognized constellations, the constellation of Orion, visible both in the southern and northern hemisphere. So we have Orion, the hunter in the Greek mythology. So here we have Betelgeuse, the red giant part of Orion, that has been given a lot of news in the last couple of years because it has been changing its brightness. and we actually expect this star to explode as a supernova in the next 100 years or so. So any change in brightness is usually very interesting. Also over here we have Orion's belt, or this is known in Chile and other South American countries, Las Tres Marias. And over here we also have Orion's Nebula, a star formation zone. Next to Orion, the hunter, we have his hunting dog, the Canis Majoris constellation. And here we have Sirius, the brightest star not only of the Canis Majoris constellation, but the brightest star in the night sky. The only other brighter of the in the night sky will be the moon, some of the planets, and well, during the day, of course, the sun. And over here, a bit closer to the horizon, we have here Taurus, the bull. So these are the horns of the bull. And over here we have the Pleiades, an open star cluster, and a favorite object of amateur astronomers. So in the Greek mythology, Orion was the hunter, and he was put on the sky punished by Artemis, the goddess of hunters, because he hunted or tried to hunt one of his sacred deer, or at least that is the version that I have learned. So she put them on the sky, and she modified all the different animals that he has hunted during his lifetime. So he's also being chased by the scorpion that is somewhere over here. Now, let's look at some of the things that we can only see in the southern hemisphere. So we can start by these two things over here. These are, of course, the Magellanic Clouds. So we have the big Magellanic Clouds and the small one. And we can actually use them to identify the southern direction. So unlike in the northern hemisphere, there is no bright polar star here. But what we can do is we can make a triangle using the Magellanic Clouds. And here in the missing vertex of the triangle, that will be the southern celestial pole. And directly below, we get the southern cardinal direction. Another way that we can do that is using the Southern Cross constellation. And that is one over here. It's the smallest of all the constellations. And what we do is that we take the large stick of the cross and we extend it 1, 2, 3, 3.5, some people say 4 times, and then we reach again the same position on the sky. Over here we also have the Centaurus constellation. You have here Alpha and Beta Centauri, and Alpha Centauri is the closest stars to, well, Proxima Centauri is actually the closest star, but it's part of the Alpha Centauri system that is a triple star system. And lastly, before we finish our beautiful view of the southern sky, there's of course we have here the spiral arm of the Milky Way. And let's mention some of the cosmovision that the natives of this area used to have. And for them, the Milky Way was a river. And to this river, the animals come to drink water. And for example, we have over here a llama. So we can see here the neck of the llama, his mouth, this part that is one of the eyes, we have the ears over here. And depending on the time of the year, we can also see part of the body of the llama. So this llama was here coming to drink water in the river. And there's also a bird, a snake, and some other constellations that I don't know that well. So I hope you have enjoyed this beautiful view of the night sky.
We have a
And,
question, an interesting question about that the Milky Way galaxy.
mhm.
Um, the question say, is that true that the stars, extragalactic objects, etc., that are behind the bulb of the Milky Way, why will not be able to be seen in any telescope? And that in conclusion, the shape of galaxy in that direction will be known forever. Middle,
Oh
I
yes,
think.
so it's sometimes for some different projects, the entire Milky Way arm is an exclusion zone. You don't even try to observe there because you're not going to see them. Now, you can see, so here with visual light, we cannot go past these very dense gas and dust regions like over here. This is the cold sack in the Western mythology. And this is a lot of dust that is obscuring the light that's behind it. But if we use, for instance, infrared astronomy, we can see what is not necessarily infrared, but we can switch to infrared, to X-ray, to ultraviolet, and see this in different wavelengths, and they allow us to see different things, and in some cases go beyond what we can see with our own eyes. But yeah, for things that are behind the Milky Way bulb, well, that is a sun that is very bright and is very filled with objects that something that is behind it is unlikely that we will able to see it. Some
And that is all the question have. Thank you for Jose to leave your comments, the question. And the people see us, you can leave the comments, greetings, everyone you want to see in the virtual tour. Every Saturday have a virtual tour. Today is in Paranal, the next week in La Silla, and the next week is in Paranal again, in Spanish and English, intercalate. So you can come and see and leave your questions, everybody, uh, whatever you know about the astronomy, the galaxies, the space. So thank you for the question today. What is the last part of the visit, Hector?
okay, so we return to the day first, and now we go to the base camp. So here we're at 2,600 meters above sea level in the summit of Paranal Mountain, and now we're going to go down. If I recall correctly, this is 2,200 meters above sea level. And here we have the base camp, and this is a mini city in itself. Here you have everything you need. You have a hospital. You also have uh, some workshops to do maintenance, repairs, or to build new things for the telescopes. You have places where people live. You have a gym over here. You have IT support, etc. Everything you need. And we are going to go to the residencia. So the residencia is the building where astronomers live while they are here. So before we go inside, let's first take a look around here. So you have here the desert landscape. That could be very beautiful, but also a bit monotone at times. And we can see how arid this place is. It's very little green here. But if we go inside, and this looks like we're going underground, but no, the building is actually built on the side of the mountain. And this building has won some architectural awards. So here we're inside the residency, and you can see here a lot of green. And this is not just to give the people something nice to look at that can have some psychological benefits. But here, this green sort of tropical garden plus the pool, this was all designed and intended to increase the humidity inside the building because outside is very dry. So that is why we have a pool and we also have this tropical garden. Now, over here we have this curtain, and this is extended at nights. And unlike the curtains that we usually had at homes, that are we open them when we get to look outside, and we close everything when we don't want the sunlight to come inside our house. This is sort of backwards. We have this extended at night because what we don't want is the light from inside the building to go outside because we do not want to contaminate the scientific observations. The entire north of Chile is subject to very strict regulations regarding light pollution in order to preserve the beautiful night sky, not just for the scientific observations, but also for the viewing of everybody that can have the opportunity to go there, and also for the wildlife that lives there. Now, this building has 108 rooms that are in that direction. This is the lobby. There are also some offices. You have over here our cafeteria where we can have breakfast, lunch, and dinner. There is also a library, a music room, a game room, etc. That the people that work here, they usually work in shifts. So this could be 1 week here and then an entire week at their places. So they need everything to have some sort of normal life here. They need to have some distraction time in addition to their work time. And also, as a bit of a trivia fact, this building was featured in a James Bond movie in Quantum of Solace with Daniel Craig. And in that movie, it was the villain's lair. And we are reaching the end of our tour. So I hope you have enjoyed so far. If you have some questions, this is the last minute, so do it right now. And please, if you are interested in this type of content, share that with your friends, your family, everybody that you know that might find it interesting. You can go to our website www.eso.org and you can find this 360 tour that you can go at your own pace and not just for Paranal Observatory but also for the Sea Observatory as well. And just so you can find tons of videos and pictures that you can use for whatever thing you want to. Okay, we're reaching the end of the tour. Felipe, would you like to add something else before we leave?
Thank you for seeing us, and in the next week, maybe take La Silla, the first ESO observatory in Chile. You can come and leave everybody you want to know. Maybe it's in Spanish the next week, intercalating Spanish and English. So if you want to see in English, you to wait to 2 weeks to wait, or just come to in Spanish and answer answer the question in English. I have no problem. The guide have no problem. Thank you, Hector, for tell about the Paranal. And this is for today. Um, I I say goodbye for today, and that is for me.
Mhm. Okay, it was also my pleasure to be your guide today, and I remind everybody, in addition to these spiritual tours, there are the in-person tours that you can go for free if you have the opportunity to travel to Chile. And please keep an eye on our social networks for the dates of the next tour and to find out if it's going to be in Spanish or English, La Silla or Paranal. And I hope to see you in another opportunity. Goodbye, and please have a lovely afternoon.